A maximum takeoff weight of 8 tons turns the Republic P-47 Thunderbolt into the heaviest single-engine fighter aircraft to ever tear through the skies of Europe in the 1940s. To understand why a massive block of metal equivalent to 2 adult African elephants could reach dive speeds exceeding 885 kilometers per hour, we proceed to completely strip away its outer alclad aluminum alloy skin. The operation of making the fuselage framework transparent immediately reveals a paradoxical mechanical structure. Instead of optimizing cockpit space or weapon bays, the entire bulging belly of the P-47 is actually a giant mechanical lung. The engine block and turbo supercharger system occupy over 60% of the total fuselage volume, a design that defies all conventional aerodynamic rules to exchange for the most violent thermodynamic output. Proceeding with a cross-section cut of the aircraft's nose to isolate the mechanical heart of this flying tank. Before our eyes is the air-cooled radial engine, the Pratt & Whitney R2800 Double Wasp. This rough metal block weighing over a ton is a masterpiece of American metallurgy. 18 massive cylinders, each bearing finely machined aluminum cooling fins, to maximize the surface area exposed to the biting cold, high-altitude winds. They are arranged in 2 concentric circles, creating a total combustion chamber capacity of up to 46 liters. Rotate the solid forged steel crankshaft clockwise to observe the heartbeat of this mechanical core. Whenever the alloy piston compresses the 1 to 100 octane aviation fuel mixture at maximum pressure, an electric spark ignites the combustion chamber, generating a brutal thrust. The continuous combustion process creates shock waves inside the chamber, translating into massive torque, spinning the 3.9-meter diameter Curtiss electric propeller. Total power output reaches between 2,000 and 2,800 horsepower, depending on the variant. This violent pulling force is equivalent to a railway locomotive forcing the 8-ton fighter to rocket into the sky. However, at an altitude of 12,000 meters, where air density is less than a third of that at sea level, a naturally aspirated engine would instantly suffocate. This is when the turbo supercharger system, hidden under the belly, intervenes. Let's follow the flow of the exhaust gases. When the exhaust valves of the 18 cylinders burst open, the fiery exhaust gases at temperatures over 800 degrees Celsius are not expelled into the environment. Instead, they are forced into a system of high-strength, heat-resistant steel piping. Isolating the exhaust system reveals a heat-generating tunnel running the entire length of the fuselage, weaving through the mechanical structure compartments, heading straight down to the tail section. An extremely dangerous design blind spot appears right at the cockpit area. This red-hot exhaust pipe lies less than 30 centimeters from the pilot's seat. To prevent this massive thermal energy from incinerating the operator and detonating the surrounding ammunition compartments, engineers had to wrap the entire exhaust system in a special thermal insulation bulkhead combined with a passive metal cooling fin system. At the tail compartment of the aircraft, the high-pressure exhaust stream directly impacts the alloy steel blades of the turbo supercharger assembly. Microscopically analyzing this drivetrain, we measure the turbine shaft spinning at an extreme speed of up to 20,000 revolutions per minute under scorching temperature conditions. The metal structure must endure immense centrifugal forces capable of tearing apart any inferior material. This rotational kinetic energy is transmitted straight to a coaxial centrifugal compressor. This compressor acts like a giant vacuum cleaner, frantically sucking the thin and freezing minus 50 degrees Celsius air from the outside environment inward. The compression forces oxygen molecules closer together, increasing air density, but simultaneously pushing the intake airflow temperature to dangerous levels. If this hot airflow is fed straight into the combustion chamber, premature detonation would instantly shatter the entire cylinder assembly. Therefore, the intake air continues to be forced back towards the front of the aircraft, passing through a massive intercooler unit located right under the main engine. Here, the intake airflow is suddenly cooled before being rammed straight into the carburetor and distributed evenly to the 18 combustion chambers. This closed-loop aerodynamic breathing structure is the core secret helping the P-47 Thunderbolt maintain 100% of its destructive power, even when operating in the stratosphere, where the Focke-Wulf 190S of Nazi Germany began to show signs of stalling and losing lift control due to severe oxygen deprivation. How could an 8-ton machine, equivalent to the weight of 2 adult African elephants, survive dives at speeds approaching Mach 0.8 without having its wings torn off? To answer this physical limit problem, we proceed to switch the display surface to technical blueprint grid mode, completely stripping away the outer duralumin aluminum skin of the main wings. The internal load-bearing structural framework immediately reveals itself. Instead of a minimalist design to reduce weight, Chief Engineer Alexander Kartveli crammed a terrifying amount of excess material into this frame. Observing the cross-section of the wing, the main I-beam spars forged from high-strength metal form an extremely rigid box structure. A network of load-bearing ribs and diagonal steel bracing, densely interwoven along the 12.9-meter wingspan, creates a mechanical skeleton capable of withstanding loads exceeding 1.5 times the theoretical destruction limit. When this flying tank executes a sudden nose-up maneuver, from a dive at a speed of 885 kilometers per hour, the acceleration force variance can spike to 9 Gs. At this moment, aerodynamic pressure violently bends the wings, but the massive I-beam structure absorbs and completely neutralizes the tearing forces, keeping the entire hull structure intact. This extreme rigidity turns the Thunderbolt's bulky weakness into an unparalleled kinetic spear, extracting combat parameters and putting the machine into a simulated environment for a direct confrontation with Nazi Germany's Focke-Wulf FW-190 fighter. The FW-190 possesses a lighter weight, greater agility at low altitudes, and superior climb rates. But once entering a vertical dive trajectory, the 8-ton weight of the P-47 combined with gravitational acceleration creates an unstoppable plunging momentum. Aerodynamic drag is completely crushed by the absolute mass and the violent pulling force from the 3.9-meter diameter propeller. Any German pilot attempting to tail this flying tank in a dive faces the risk of their wings snapping before they can even pull the trigger. However, speed is not the only physical shield. Establishing a longitudinal cross-section covering the entire cockpit area to analyze its survival principle. Hidden beneath the front windshield is an impenetrable structure, designated by the U.S. military as the armored bathtub. The entire pilot seating area is enclosed by a system of reinforced steel bulkheads up to 12.7 millimeters thick. The backplate, floor plate, and headrest armor are responsible for completely neutralizing the penetrating kinetic energy of shrapnel from nearby exploding flak anti-aircraft shells. But paradoxically, the greatest shield of this fighter is precisely its mechanical heart. By placing the 18-cylinder radial engine, weighing over a ton in front of the cockpit, engineers inadvertently created a meter-thick solid metal wall blocking direct fire. Let's observe a contemporary technical counterpart, the P-51 Mustang fighter, equipped with the liquid-cooled V-12 Merlin engine. It only takes one 7.9 2mm rifle bullet, piercing the fragile liquid cooling pipes located under the Mustang's belly, for the entire sophisticated engine block to overheat, seize its pistons, and catch fire in less than 3 minutes. In contrast, the air-cooled R2000 800 engine of the P-47 features a hollow distributed structure and independent operation among its cylinders, initiating a real-world ballistic collision scenario. Two 20mm German artillery shells pierced straight into the aircraft's nose, tearing apart and completely blowing away 3 front cylinders. Combustion pressure in the blocked area drops to 0, lubricating oil sprays along the fuselage walls. But the remaining 15 cylinders continue to suck in intake air, compress fuel, and maintain a continuous explosion cycle. The massive forged steel crankshaft still roars and spins despite intense mechanical vibration, transmitting enough kinetic energy to drag the bullet-riddled aircraft and its pilot limping across the English Channel to a safe base. Using mass to crush agility, using material thickness to neutralize damage, the redundant steel frame combined with an engine block that cannot be killed by a single slash defined a physical stubbornness unprecedented in military aviation history. Without the need for complex 20mm or 30mm cannons, the P-47 Thunderbolt design team chose to obliterate targets using pure physical firepower density, executing the removal of all duralumin aluminum cover plates on the surface of both main wings. A massive weapon system is instantly revealed, filling every structural void outside the landing gear bays. 8 12.7mm caliber heavy Browning M2 machine guns are evenly distributed on each wing. Behind them are stamped aluminum ammunition trays, holding a total of 3,400 armor-piercing and tracer round. The total weight of this weapon and ammunition system alone reaches nearly half a ton, proceeding with a microscopic projection into the loading mechanism of a Browning M2 located near the wing root. When the trigger is squeezed, the automatic gas-operated system combined with the recoil spring operates at extreme intensity, forcing the bolt carrier to cycle continuously. The cycle of recoiling, extracting the shell casing, loading a new round, and the firing pin striking occurs at a rate of 800 rounds per minute for each gun. The dynamics of the 8-barrel cluster firing simultaneously creates a terrifying recoil force, but the aircraft's 8-ton fuselage completely absorbs this vibration, helping the bullet trajectory maintain absolute stability, establishing the firepower convergence point on a 3-dimensional spatial map. All 8 gun barrels are aligned inward at a microscopic angle so that the trajectories of the projectiles intersect at a point exactly 275 meters ahead of the nose. At this bullseye, a kinetic chainsaw is formed, analyzing the total kinetic impact energy generated when hundreds of carbon steel core bullets travel at a muzzle velocity of 890 meters per second, raining down on the target in less than 3 seconds. This violent firepower density not only severs the wings of German interceptors, but is also powerful enough to shred armored trains or even pierce the top armor of a Panzer IV tank moving on the ground, placing the machine into a dense anti-aircraft fire environment over the skies of Europe to measure its ultimate physical endurance. A combat scenario is recreated. 20mm German flak fire hits directly. The aluminum skin is torn open. The exploding shells completely blow away 2 of the 18 cylinders of the R2800 engine block at the front nose. Lubricating oil sprays out, catching fire into a long trail along the fuselage. For any other machine, this is a death sentence. But the hollow distributed structure of the radial engine takes effect. Combustion chamber pressure at the blocked area drops to 0, but the remaining 16 cylinders stubbornly maintain the intake compression combustion exhaust cycle. The massive forged steel crankshaft still roars and spins despite violent dynamic imbalance, transmitting enough energy for the Curtiss electric propeller to continue biting into the air, dragging the aircraft bearing dozens of holes limping across the English Channel back to a safe base. America's extreme mechanical design philosophy was perfectly proven. Using mass to crush agility, using a miraculous turbo-supercharged respiratory system to maintain power in the stratosphere, and equipping absolute firepower to turn the tide of the battlefield. This flying tank crushed the skies of World War II with its very own physical roughness and stubbornness. However, Can this armored shield and massive piston engine block still hold the throne when facing an entirely new generation of dynamics? A machine that completely eliminates the propeller and replaces it with the jet thrust of hot gases? Don't forget to subscribe to the channel and leave a comment, because in the next video, we will strip the skin off humanity's first jet monster, the Messerschmitt Me 262.